All right. Hello and welcome to another physics video lecture. Today, we're going to be talking about light wave behavior. Now, we've already talked about wave behavior in the past. Today, we're going to be building on that and talking about certain behaviors that are special to light. All right. Now, let's start off with this picture you see in the background here. Now, I'm sure you've seen some form of this before. You may recognize this as a moving version of Pink Floyd's Dark Side of the Moon cover, which is an amazing album. Or you may know that this is a prism creating a rainbow. This is an effect that I'm sure you've seen in your life. If you've ever seen a prism or you've ever seen a rainbow after it rains, well, where does that come from? Rainbows are created through something called dispersion, all right? If you know the word disperse, you know it means to spread, right? And that's exactly what's happening here. So what happens when white light is pure light. It's light that comes straight from the sun, okay? When that light hits a prism, what happens is that all of the different colors, okay, they all slow down, all right? And they do so because they all have different speeds when they go through either a liquid or a solid like a prism, okay? And what happens is because red has the longest wavelength, it slows down the least, okay? Whereas violet slows down the most because it has such a short wavelength. So here, if your question is, which color is dispersed the most? Well, you have to see which one bends the most. And the one that bends the most, it goes all the way down to violet. So violet bends the most because it has the shortest wavelength. And again, this is the same thing that happens. This is why you see rainbows. Rainbows happen after it rains, when it's sunny outside, because the sun is going through all of those water droplets and the white light is going through, okay? It's separating, and all of those different colors are all moving at different speeds inside of the new medium. Pretty cool, right? All right, now, when you are shopping for sunglasses, you usually have lots of options, but one of the big questions is, do you want polarized or non-polarized lenses? And I'm here to tell you, always opt for polarized lenses. Here's why. Polarization is a process that exists because light waves are special. All of these electromagnetic waves that we're talking about, they don't just vibrate in one plane. They don't just vibrate up and down or left and right. They're really special, and they're vibrating in many, many, many different planes all at the same time. They look like this. So they're vibrating up and down, left and right. They're vibrating at diagonals to each other. They're all over the place, okay? And what polarization does is it puts the light through a filter, okay? And these filters are really simple. Here, if you can see it, you can see that these stripes are going up and down, okay? That means that we have a filter that's vertical, whereas here, the stripes are going side to side. This is a horizontal filter. So what happens to the light as it goes through? Well, this light, which is vibrating up and down and left and right and diagonally, when it goes through this vertical filter, the only vibrations that come out of the other side are vertical vibrations, right? We're left with a single plane of light, okay? Now, when you take a vertical vibration and put it through a horizontal filter, what comes out? Well, nothing comes out. Yay, nothing comes out because the vertical wave is blocked by these horizontal filters, right? The wave's going this way, it hits this, right? And nothing's able to come out, okay? This is what polarization is. So whenever you see polarization sunglasses, what they are is they're sunglasses that have little tiny filters for the light. Again, horizontal filters block vertical waves, and vertical filters block horizontal waves, all right? These vertical filters, these are what we find in the sunglasses, okay? And they're great. Again, here's a moving version of this. You can see the light, it's going up and down, it's going left and right, it's going in a diagonal, but here we have a vertical filter, so the only thing that comes out is a vertical wave. And this causes a huge difference, okay? So the difference between the two, you can see right here. With a non-polarized lens, what happens is that those horizontal waves, they actually cause glare whenever they bounce off of the road. Okay, if you've ever been driving, maybe you've seen that glare coming off the road. That polarization eases it, and it's like a weight is lifted off your eyes. Okay, polarized sunglasses make your eyes go, oh, they're so nice. Okay, so again, here's just another, right? Here's what it looks like with the glare, and again, you can see that the light is bouncing off of the surface. It's vibrating at all these angles, and you have that glare going in. The polarized lenses block a ton of that light, so you get this really clear, crisp image, and that's because polarization filters the light into a single plane. All right? A good way to test if polarized sunglasses really are polarized, if you're at the beach or you're on vacation, maybe somebody's trying to sell you a pair of polarized glasses, you're not 100% sure if they're lying or telling the truth. Well, what you can do is you can take two pairs of polarized glasses, and since they both have filters, if you put them at 90 degrees to each other, like this, you should see pure black. It should completely blacken out, just like you're seeing here. Because again, those filters will block out, if you have a vertical and a horizontal filter right at 90 degrees to each other, they should block out everything, which is pretty cool. All right, the next thing I want to talk about is to go back and talk about diffraction. Now, we've already seen this, and hopefully you remember, diffraction is when a wave bends because it goes through a small opening or because it goes around a corner, all right? And in both of these cases, this causes the wave to bend. This is diffraction. The smaller the opening, the more bending we see. And this is really easy to understand when we talk about water waves or even sound waves, but light waves diffract too, okay? Now, light waves also interfere with each other, okay? What is interference? Interference is the interaction of these waves, meaning when two light waves hit each other, okay, they can either, if they have the same crests, amplify each other and have constructive interference, or if the crest of one light wave hits the trough of one light wave, they can cancel each other out, just like sound waves or water waves can. So here, what we're seeing is we're seeing one light wave coming up, and then if you can't see it here, it's going through these two openings, right? This is very important because what we see here, all right, is we have constructive interference, and what's happening is that both of these waves are bending when they come out of these slits. So where the two tops of the light waves hit each other, they make even brighter areas. But similarly, we also have areas where the top of one wave hits the bottom of another wave, and that gives us these dark spots here. Right? Let me walk you through that one more time. Okay, so when a light wave diffracts through two holes, okay, the waves spread out. Okay, so we have opening number one and opening number two, right? The waves are coming in straight, they hit the opening and they bend. Well, if these waves start to bend out and these waves start to bend out, eventually the waves are going to hit each other. And when they do, we get interference, okay? And a gentleman by the name of Young, Thomas Young, I believe is his first name, he realized this a while back, and this had profound implications on science. So his experiment was really simple. What he did was he had a light source, which was back then a candle, and he had a little tiny piece of metal that had two openings in it. Now, if you were to shine light through these two openings, most people would assume that on the wall you would see two lights, one that goes through each opening. But that's not what he saw. He saw this. He saw this band of like a dozen lights. So he saw lights and dark spot, light, dark spot, light, dark spot. And he was trying to figure out why he saw this. Well, he realized what was happening, okay? He realized that the light was acting as a wave, right? The light wave was going straight, it was hitting these two openings, and as it went through the openings, what was happening, purple marker, is that the light was bending when it goes through this opening, right? Like this. Well, it was also bending as it was going through this opening, like this. And now you have all of these areas like here and here and here where the light waves are hitting each other, okay? They're interacting with each other. Or scientifically, they're interfering with each other, okay? So what he realized is the reason that he saw all of these light spots on the wall is because these light spots are the areas where the light hit and had constructive interference. And the dark spots were the areas where the top of one wave hit the bottom of another light wave and caused destructive interference. Now again, this double slit experiment by Thomas Young, it proved that light is a wave. This is crazy. Before this, people didn't really know what light was. Okay, so this is half of the equation. Again, we shoot some electrons or some light through this double slit, and on the screen we see multiple bands. Okay, because again, what we're seeing here is we're seeing that first the wave is diffracted when it goes through the openings, and then they hit each other, and the bright areas are constructive interference, the dark areas are destructive interference. If you would like to watch a great video about this YouTube video right here is excellent. I highly recommend clicking on that in your PowerPoint presentation. So Mr. Young proved that light is in fact a wave. Now, today, the internet is much, much, much faster than it was when I was in high school. And there is a very solid scientific reason why this is true, okay? To understand this, we gotta go back and remember reflection and refraction, okay? Now, the law of reflection is a simple one. It tells us that when an incoming light wave hits something, okay, it's gonna bounce off. This is a solid object, especially a flat one, like a mirror. This light wave is gonna hit the mirror and bounce off. We always draw a normal line. The normal line is always 90 degrees to the surface, and that's because we measure our angles to the normal line. This angle right here is called the angle of incidence, and this angle right here is called the angle of reflection. And these two angles are always equal. That's the law of reflection. When light hits a surface, it's going to bounce off at the same angle. Okay? Now, the law of refraction tells us that when light changes mediums, it bends. So when it goes from a gas into a liquid, it bends. When it goes from a liquid into a solid, it bends, right? We know that light waves, if they slow down, they bend towards the normal line. And that's what we're seeing here, okay? If the light wave speeds up, it bends away from the normal line. So again, here we have a light wave coming down, and let's say this would be air, right? And down here would be water, okay? Now, we learned last class that light waves travel faster through air and slower in water because air is less dense. Remember, light travels the fastest when there's the fewest amount of atoms in its way. Fewest, is that a word? So when the light wave goes through the air and it hits the water, it slows down. And like I said, when it slows down, it wanted to go this direction, right? But it's gonna bend towards that normal line. Bends towards the normal line when it slows down. So just to not leave you guys high and dry, I included both of these. Refraction from a less dense to a more dense medium. This is like going from air into water. It bends towards the normal line, okay? Because it's slowing down. Okay. And when it goes from a more dense medium to a less dense medium, going from the water to the air, it goes away from the normal line because it's speeding up. Now, because we know this, we can learn about something new. This is only true of light waves. This is something called total internal reflection. What the heck is that? Okay, total internal reflection is when you have the complete reflection, okay, of light at the surface between two mediums. So example, if we have a medium change of going from air to glass, okay? Now the first rule is that in order for total internal reflection to work, it has to go from a dense medium to a less dense medium. So we have to go from glass into air, all right? So what does this look like? So, and this is crazy to see, and I'll show you a video in class, but when you are shining light from glass, like in a prism, to the air, what'll happen is at most angles, that light will bend away from the normal just a little bit, right? Notice it wants to go this way, it bends a little. Going out of the glass into the air, it goes this way. Going out of the glass into the air, it goes this way. And notice this angle keeps bending and bending and bending. Well, what happens is eventually there's something called a critical angle. And this is the angle that when it hits, whatever this angle is right here, when it hits the glass, it doesn't refract anymore. It doesn't come out anymore. It is completely reflected. It is totally reflected back inside. Total internal reflection. So look here, this is crazy, okay? This means when you shine a laser at this angle, at 30 degrees, you know what happens? It bends a little. You increase this angle a little more, it bends a little more. Here, we've increased the angle so much that now nothing is coming out and all of that light is reflected back, okay? You're stopping refraction and now you have all reflection. Now, why is this important? Why do we care? Well, because what that allows us to do, and watch this, see how when he bends that light up, see how it right there? You see how it's going completely inside and it's bouncing back and forth? Total internal reflection allows us to use things called fiber optic cables. And these are cables that have a little bit of glass on the inside and we can shine light through them. That light is shined at an angle so that it bounces back and forth, okay? And it completely stays within the medium, okay? Fiber optic cables revolutionized telecommunications and the internet. They allowed us to stop sending the internet over phone lines, which is what we did when I was in high school, and now we can use these fiber optic lines, which is amazing, okay? But we use this for a lot of things. We use it for the internet, we use it for medical imaging, we also use it for any kind of touch screen. So your cell phone, your iPad, all of that is due to total internal reflection, right? If I go back here, again, you can see it right here. The light goes in, and then it's able to bounce back and forth through the cable and send the information using light, which again is 1,000,000 times faster than using sound. Pretty cool. Okay. Oh, also, if you've ever seen these things at like the fair, that's total internal reflection. The light is bouncing through these fiber optic little strands. All right, last but not least, hopefully you guys remember this right here. Do you guys remember the name of this? Well, we saw this when we talked about sound, right? So when an object producing sound is moving, the sound waves in front of it smush and the wavelengths get shorter, meaning we have a higher frequency and a higher pitch. And behind it, the wavelengths get stretched. So we have a longer wavelength, a lower frequency, and a lower pitch. This is why when a fire truck is driving past you, you hear a high pitch as it comes towards you, woo, 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 and a low pitch when it drives away from you, woo, woo, woo. Well, I guess it'd be going this way. So on this side, woo, 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 woo. Okay? This is called the Doppler effect, okay? And guess what? It works with light as well. This is crazy. So what this means is that if a source of light is coming at you, the same thing is happening, okay? That source of light is coming at you, the light waves in front of the object are smushing together, okay? Causing the frequency to increase. And as it goes away from you, it causes those wavelengths to get longer, okay? And it causes the frequency to decrease. Now with sound, frequency equals pitch. With light, frequency equals color. So this is cool. So what this means is if an object, like let's say a distant star that's like thousands of light years away, if that star is moving away from you, the white light that's coming out of that star will actually look red. Again, the reason is because the wavelengths are getting longer, right? And red has a long wavelength, right? Low frequency. But if the light is coming towards you, right, like the fire truck, well, all those wavelengths are going to get smushed together. So you're going to have smaller wavelengths, higher frequency, okay? And you're going to see a higher frequency color, like blue. And that's what we call these, okay? We call them red shift and blue shift. And this is nuts. This is how we can tell if galaxies hundreds of thousands of light years away from us are either moving away from us or towards us. When we look at them, if they look red, we know that they're traveling away from us. And if they look blue, we know they're traveling towards us. And this is actually how we know that the universe is expanding. Because when we look far away in the universe, all the light we see is red, meaning we're seeing longer wavelengths and things are moving away from us. So again, same thing here. If this is the sun and it's moving to the right, the person that it's moving towards will see a high frequency and we'll see bluer or more violet light. And the person that it's moving away from will see longer wavelengths or lower frequencies, and we'll see red light. Okay, pretty cool. Again, same thing here. If it's moving towards, it looks blue. If it's moving away, it looks red. All right, guys, that is it for light wave behavior. As always, please use your notes to complete the DOL. If you have any questions, you can either email me or find me at tutoring. All right, guys, be good.